Hi, I'm Stephen Jones, and I'm one of the architects of CUDA. Every GTC for the past few years, I've given a talk on what we've been working on and what's coming up, and there's always way too much to cover. But I think it's really important to take a little time to explain not only what we're doing, but why it's happening. Because I think the why is so fundamental to understanding what's going on. So with that in mind, I'm going to actually start by talking about some history, something I call the 3 eras of computing. Starting at the beginning, the first era of computing was single-core, single-thread programming. Programming is literally taking a problem, breaking it down to a series of logical steps that a computer can understand. So we'd write straight-line code, and it was tuned to run on a processor as fast as possible. And for data, we just iterate over the data linearly in the most efficient way that we could. We'd tune individual instructions, getting things a few cycles faster. It was like the good old days of hacking code. So those of us who were programming in the 80s and 90s will remember the gigahertz race. This is when silicon logic got smaller and chips just got equivalently faster. Our code just sped up just by magic every new generation. This was thanks to something called Dennard scaling, named after Robert Dennard, who figured out that as you make transistors smaller, you can run them faster without increasing the power. So life was good. Until it wasn't, right? What happened was, as history well knows, quantum mechanics stepped in. It said, nope. And transistors got so small, things like quantum tunneling started to leak power. So we no longer could shrink logic for free. And so around 2007 or so, the frequency of processors leveled off. The free performance gain was over. So instead of making a computer faster by increasing the clock frequency, designers had to switch to adding more cores, right? Moore's law was still improving, so you could keep packing in more transistors, but you couldn't make them any faster. And so the only way to keep your program scaling with the technology was to start using more of these cores. Any individual core wasn't getting any faster. And so this brings in what I think of as the second era of software development, right? Where you had to run multiple things at once to take advantage of technological improvements, right? It's the parallel programming era. It's been a long time since you could buy a single core CPU. Your phone probably has 6 of them. So all programs now have to think about how they target multiple cores, multiple threads. Now, to some extent, multi-core is trivially handled by just running lots of single-thread processors at the same time on the different cores. Right? Your computer you're watching this on right now is probably running 100 processors all at once, multiplexing them across the cores in your CPU. But that's not really parallel programming. That's not making one application run faster. That's just doing more things. So to make an application actually run faster, right, for it to keep scaling up performance as Moore's law keeps scaling the silicon, we all had to adapt our algorithms. Right? We had to become multi-threaded. This is something supercomputers have been doing for years, but it's moved into the mainstream now. And so you had to think about how to break down your data into separate elements, right? It's not a matter of just iterating across them. You want them to be processed independently at the same time. This is data parallelism. Or you take your program sequence and you'd be trying to find independent sections which could operate concurrently. It's no longer straight line code. That's not good enough. But so I want to break it apart into pieces and synchronize and exchange data only when needed. So this is something called task parallelism, and it's based on asynchronous execution. You probably think of it as multi-threaded programming, and you'd be absolutely right that is an example of task parallelism. Right? By identifying dependencies in the workflow, and really importantly, independencies, where things can run concurrently, task parallelism does within your program what those multiple processes are doing on your operating system. A really important point is that data and task parallelism are not mutually exclusive. Right? An individual task is often data parallel in and of itself. So this task graph on the right-hand side is actually as a hierarchy of parallel work. Right? I've got task parallelism, and then within that, I have data parallelism. Now, if you're a deep learning expert, you probably recognize this thing on the right of the famous transformer network. And if you're thinking right now that you would never be processing a flower, that yes, you're right. But I'll ask for some artistic license. I'm really trying to portray the concept that data parallelism is very often nested within task parallelism. You often get both at the same time. And it doesn't just stop at multi-core. Individual chips are no longer the granularity of computing. Just like every processor has multiple cores, every node has multiple processors. This is the HGX 8100 server for data centers, and it has 8 GPUs on it. And every system has multiple nodes, multiple racks. Right? We've reached the point of data center scale computing. This isn't the GPU system of tomorrow. This is the GPU system of today, right? This is where my third era of computing comes in. When we went multi-core, to keep scaling, it became important to take advantage of parallelism. Right? You needed to spread across those cores because each one wasn't getting any faster. Now that systems are growing to such scale, to keep on scaling, it's becoming important to take advantage of locality. This isn't new, right? Ever since multi-core systems have existed, people have been taking care to control affinity of their process so that the core that you're processing on is attached directly to the memory that you're working with. Right? Just like parallelism moving from supercomputing to the mainstream, locality is now moving from high-performance computing also into the mainstream. So as my core count and my node count increases, there's really two things that I want to think about. First, it becomes expensive to move lots of data around, both in power and in time. Right? So I want to minimize data movement. And equally importantly, but maybe less obviously, it starts to be really advantageous to not synchronize the world. Right? You want to synchronize as locally as you can get it. If I have to synchronize with some other threads to exchange data, and I have thousands or millions of threads in my system, I don't want to sync with everyone. Right? I want the data exchange to stay local, and I want the data exchange to stay close, so that synchronization is as fast as possible. Right? This is a real benefit to keeping it local, is not having to stretch out across your whole system just to do a handshake. So to get the most out of the processes of the future, I need to take advantage of locality, as well as dependency-based parallelism. That's not going away. This is an extra thing, right? My third era is the era of locality-aware computing. Where I place things is becoming as important as when they run. And I need to think about both of these things in some way. This is true at every level of the hierarchy, right? Whether I'm running a task parallel sequence of operations on a small GPU or a big data center, I want to keep the green parts together and I want to keep the blue parts together instead of spreading them around randomly. And that means that then my data and my synchronization, everything is much more local. But so what does this mean for how I program these things? Right? What does data center scale computing mean to an engineer or a scientist or a developer? Well, for a start, I don't want to have to think about it. Right? I want to describe my problem at the level of the hierarchy that makes the most sense for my work. Right? If I'm an AI researcher creating a neural network, I want to draw this transformer graph and not care what happens inside each task. I leave that to the framework. And if I'm a framework developer creating a system based on linear algebra, which is very typically the case, I don't care how a tensor contraction is implemented. I leave that to the library developer. And as a library developer, I don't care how the threads are created or how the work is submitted to the hardware. I'm going to leave that to the runtime. So this is how software already works, right? It turns out that the parallel era of computing didn't end up requiring everyone to learn parallel programming. Some of us did, but most of us don't. It just required working with a hierarchy of frameworks and libraries and runtimes, where each level of the hierarchy zooms in a little more closely to the system. You just want to target the bit that makes sense for your problem and not have to think about the rest. You want just that to support you automatically. So what we're talking about is scaling, right? And what we need to do to address it. It's the when and the where. And I think there's really two dimensions to this. There's the way that you scale task parallelism, where you want to both schedule based on the dependencies and use dependencies to say where things go, and placement based on the data flow that happens within the graph. I want my producer and my consumer probably to be placed in the same location so that the data doesn't have to move very far in order for them to hand off that data. The second dimension is the data parallel aspect of this. Right? For data parallel workflow, I care about streaming work through the machine as fast as possible. I want to fill every gap. I want to keep the machine as busy as possible. It's all about crunching all the data in the shortest possible time. But I also care about placement of that data. And I care about shared data. I care about data reuse because that affects how efficiently I can crunch the data, how fast I can run through this. Right? Most programmers know that they want their data in cache if possible, not in memory. Right? Or in memory rather than over the network, or over the network instead of on disk, and on disk rather than over the internet. Right? You probably instinctively localize your resources whenever you write software, and you explicitly write code intentionally to be localized. What I'm saying is that to control the machines of the future, or even the data center scale machines of today, we need to start enshrining locality as fundamentally as we enshrine concurrency when the multi-core revolution happened in the 2000s. So with that said, let's change gear for a moment. Right? Obviously, this isn't going to be unrelated, but the big announcement today is the Hopper H100 GPU. And obviously, it's going to have a profound impact on the CUDA language and the platform. My colleagues Michael Andersch and Greg Palmer just gave a talk earlier today on the architecture of the H100. I've linked it down below. If you've not seen it, you want to see it. There's a ton of stuff in Hopper. I don't have time to go over all of it. I'll try and scratch the surface. Even this list is just the beginning. The heart of Hopper, of course, is the new H100 SM. This is a big part of where the magic happens if you're a CUDA programmer, but by no means all of it. It's not only bigger, better, faster, more. There's actually some profound new architectural features which change the way we program the GPU. Right? It takes the asynchrony steps that we started making in the A100 and it leaps them forward. And I'll explain what it's done and why. But first, though, I was looking back at some history, and exactly 10 years ago, I stood on stage, back in the good old days when we actually stood on stage at a conference. I stood on stage and I introduced the Kepler architecture at GTC. This was revolutionary state-of-the-art in 2012. It had 15 SMs. It had over a teraflop of double precision floating point performance. It was an amazing chip. I used it for years. From 10,000 feet, Kepler and Hopper look very similar when you compare the full chip block diagrams like this. The numbers show the difference, though. This chip is actually an order of magnitude bigger. It's got 132 SMs to Kepler's 15, and 15 to 20 times the performance. In fact, if you put them next to each other at the same scale, the Kepler GPU actually fits nicely in just one corner of the H100, right? The hierarchy of scale story that I was telling you earlier applies all the way down into the chip here as well. Right? This is almost like Kepler is the node to Hopper's data center in some way. This, though, is the reason why a program written 10 years ago for Kepler still runs well and over 10 times faster on Hopper, right? Because this ability to scale across SMs is at the core of the CUDA programming model. It's carried us from 15 SMs all the way up to 132. But it does feel a bit like it's going from a node to a data center at this point. So let's recap the core programming model for a moment. I start with some work to do, right? My favorite image of a flower. Obviously, as you can tell, I love this flower. There's going to be a whole lot of the flower in the talk. But yeah, so we're going to do some image processing on this flower. What you do is you divide it into many blocks, right? This is called the grid of blocks. This is the fundamental element of CUDA. Each block is run on the GPU like it's a completely separate program. And the GPU runs as many of these as it can at once. Up to several thousand of these run at once. This is a big place where the massive parallelism comes in from the GPU. Usually, there are more that will fit in your grid. Your grid is usually more than a few thousand blocks. And so as the one finishes, a new one will start. But each block has to run independently. You don't know what order they run, where they run, who's next to what. They're just independent pieces of work. And then independent blocks work on their own fragment of a problem. They've got threads in them, and the CUDA hierarchy is therefore grid to block to thread. Often you'll iterate many times, relaunching the grid or a sequence of grids in a loop until the final result's achieved. And this is generally how CUDA programs run. What's new in Hopper is because its massive scale means we've taken the concept of a grid that's made up wholly of independent blocks of work, and we've added a new tier of hierarchy. This is called the thread block cluster. It's a block of blocks, if you like, right? Block 2.0. The new way to think about blocks in your program is that I still have my individual blocks, but we've got a way to target a localized subset of a grid in a way that opens up more opportunities for programmability and performance, right? This is the locality story I was just talking about. And the locality is reflected in the hardware. It's the entire point, right? The blocks within a thread block cluster all live in what we call a GPC, a GPU processing cluster. It's a collection of SMs which are physically adjacent to each other on the silicon, right? This is the thing that's the same size as the whole Kepler GPU. So a cluster represents literally a Kepler worth of parallelism and even more performance than that. But this is the locality I was talking about. This is where it comes in. By adding a cluster to the execution hierarchy, we are allowing an application to take advantage of faster local synchronization, faster memory sharing, all sorts of other good things like that. So here's how a cluster works. We've added another tier to the programming model. A cluster is like a big block full of blocks. That means you can have, since you can have 16 blocks in a cluster, you can have 16, 3, 8, 4 concurrent threads all working together, all at the same time in a cluster. Just like a block, they're all guaranteed to be running concurrently. They're actually guaranteed to be running on different SMs. More on that in a moment. And so it's a block on steroids, right? And the code that I'm showing here is using CUDA's hierarchical programming model called cooperative groups. I'll review that in detail in a minute, but hopefully the text there is obvious enough to convey the idea. The really important part is that we're moving in the direction of annotating kernels with the sizes and resources that they need. right? I think this makes a lot more sense than having the CPU launch code to do it. You can, of course, still do it that way, but I love the idea of attaching to my kernel that knows the resources it requires the ability to say, I want to run a cluster of 4x2 blocks, right? I like it so much, I think we'll probably be adding for block size as well. So you've got a lot more threads now which can work together than you used to have, which is great if you need it, but you don't have to use it if you don't need to. You can stick with one block. You can size your thing to be the smallest cluster that you need. The whole point is that you target the level that makes sense for your application, right? Like the difference between the researcher and the framework developer and the library developer I was talking about. You shouldn't have to think about anything other than the size that makes sense for you. So to carry on the analogy, and it's much more than just an analogy, it's an equivalence. The cluster, this block of blocks, has all the properties of a CUDA thread block, but bigger. Every block in a cluster can read and write the shared memory of every other block in the cluster. We call this distributed shared memory. Note that DSMEM is not new memory. It's not an extra memory space that's added on. You literally have access to the shared memory of other blocks. It's scaled up shared memory for the scaled up block. Another thing to point out is that a cluster places blocks each on their own SM, as I mentioned before. Right, so there's a lot of good reasons for this, but one of them is to maximize the shared memory. It's also about getting parallel bandwidth into the memory system and other things as well. Here's a quick example of how I can use it. I can declare a shared variable X. And remember, every block runs the same code, so every block has an X. And I can map the X from other ranks as well. So everyone has an X. So I can go and get a pointer with this map shared rank function to rank number 2's X, and then I can write to it explicitly. The other thing to note is that distributed shared memory is what we call PGAS, Partitioned Global Address Space. Right? That means you don't get a contiguous range of addresses like a single giant memory, but you actually get chunks for each block in the cluster. Right? We do that so that the sizes can change and the strides are well determined. We're looking at exposing an analytical way to get the base pointer, but for now you query the rank, and the rank query is hardware supported and really fast. So this is an example problem that I borrowed from my colleagues Vishal Mehta and Guillaume Thomas Collignon. They're from the DevTech organization. They're always some of the first people to get their hands on new hardware, and they put it through its paces. And they've got a talk where they go over all that they did with Hopper, what they learned, how it works. It's amazing. I've linked it below. This and the Inside Hopper talk that I linked earlier are the two talks you absolutely have to see if you're interested in Hopper. Anyway, this is a very trivial example where they simply took a histogramming problem and they applied the benefit of the much larger cluster distributed shared memory to allow them just to do work locally instead of spreading it across the GPU. And by sharing it locally, that locality we were talking about, just paying attention to that gave them a 70% speed up compared with not using a thread block cluster, which is, it's huge. So speaking of shared memory, one thing the A100 invested in heavily was asynchronous data movement, right? Remember my two obstacles to scaling, data movement and synchronization, and I'll be getting to synchronization in a moment. But the ability to kick off a copy and then pick up the result later is a huge step towards keeping all my dependencies local. Right? It also frees up my threads to do other work while data is moving around in the background. We attached it to this command called memcopyasync, which just triggers a barrier when the copy is finished. The asynchronous copy, in fact, was possible because of this new, really powerful asynchronous barrier. We brought it in with the A100, and it's what you call a split barrier. It's where reaching the barrier doesn't mean you have to stop for everyone else. Remember how I said that as you scale up, the most expensive thing is actually waiting around to synchronize with the world, even more than just moving data. This is the solution, right? You mark yourself arrived, and you go and you do something else in the background while everybody else arrives. So Hopper is built on this barrier, and it's amazing. Right? One of the best things about my job is I sit down with the hardware people and we work out what the most valuable things are that we can build, and stuff like this comes out of it. We've added to the barrier, and this new barrier not only allows you to wait for threads to finish, but it allows you to wait for data to arrive as well. Right? My threads can now sleep waiting purely for data. They don't have to care where it's coming from, which means they don't even know who they're synchronizing with, which is what normal barriers are about. You just say, wake me up when the data's arrived. It's actually even cooler than that. I can have my thread waiting, or really a cooperative group of threads waiting, expecting data from lots of different places, and only wake up when it's all arrived. Right? So here I've got 4 people sending, and I don't care where it's coming from. I'm just asking the transaction count, let me know when I've received the right amount. But the thing that really, really makes this transaction barrier for me is that these transactions are what we call self-synchronizing writes. And this is the ability to write data to a recipient and have the recipient know that the data is ready without needing some kind of handshake. So normally I have to do a handshake where I send data and send a flag and send a fence in between them, and there's a lot of back and forth that has to go on. In this case, the asynchronous memcopy knows how many bytes it's carrying, and the barrier knows how many bytes it's expecting, and when the data arrived, it just counts itself in. Right? These are one-sided memory copies, and it's 7 times faster than normal communication because I don't have all that back and forth. It's incredibly fast because it's just a single write operation. And from the perspective of the sender, it's purely fire and forget. Right? It actually makes it faster to write data to my cluster partner than I used to get writing between threads in my same block. But obviously, I can also use this in my local shared memory as well. Right? All of this works locally in one block or between blocks in a cluster. So your data movement just gets faster and easier. So memcopy async moves a chunk of data, like most copying does, but this one-sided communication also extends to individual transactions, right? That means I can send a message, or I can up and down a semaphore, or I can manage a shared data structure, all of those things with these super fast, self-synchronizing one-sided operations, right? In particular, Hopper not only allows a data write, but very coolly, it also allows an operation to be applied atomically as something arrives. So I don't just have to write a value on top of whatever was there. I can say add 100 or take the maximum of 100 and whatever is there. Right? This is exactly what a producer-consumer system wants. Right? Instant, one-sided messaging plugged into shared data structures and atomics. I love this. This is probably my favorite feature on the GPU. All of this is actually made possible by a new piece of hardware inside the Hopper SM. It's called the Tensor Memory Accelerator Unit, which we all abbreviate to TMA because it's shorter. It takes the original memcopy async, which only used to work from global into shared memory, which was super handy, but it makes it bidirectional, and it makes it work between clusters as well. So I can go from global to shared, shared to global, DSMem to DSMem, right? It's the thing that enables all these one-sided data transfers as well, both as bulk copies or singular operation atomics, like I was showing you. I'll tell you about it in a moment, but first an example. My background is fluid mechanics, so I often think about how these problems are going to be solved in that kind of a frame. It also makes pretty pictures. But this applies to any problem that uses neighboring values to compute something. So a convolution is the obvious example, but stencils, derivatives, all sorts of things like that. Anyway, the thing about these neighbor affecting algorithms is that when I split them up, I need to communicate with my neighbors to read or write their data. Right? This makes the edges of the region expensive to work with. It's the non-local problem again. I split my thing and suddenly I've got some data that's not local to me and I've got to spend more effort getting to it. With these fire and forget one-sided writes, though, I literally treat my neighbor halo like it's local data. There's no need to synchronize or handshake. The number of transactions is known. It's the size of my halo. And a block simply knows from the transaction barrier when the data is ready. It's so simple and so fast. So let me tell you more about the TMA. The TMA is a self-contained data movement engine. That's a separate hardware unit. It's inside the SM, but it runs independently of your SM threads. So instead of every thread in the block participating in the asynchronous memcopy, the TMA can take over and handle all the loops and address calculations for you. Right? A single thread can now initiate a copy of the entire shared memory if you want. And the counting transaction barrier means that the consumer threads can simply wait for the data to arrive without ever having to sync with each other. They never even have to know what thread kicked off the copy. In fact, because of clusters, the consumer threads don't even have to be on the same SM as the producer thread, which is exactly how I want to run my task parallelism. The TMA also doesn't just do linear copies, right? It's called the Tensor Memory Accelerator because it can work on multi-dimensional data, up to 5-dimensional data. So you call it and it goes off to do the copy, which means the hardware takes over the job of calculating the addresses and the strides and checking the boundaries, all of that stuff. Right? It can cut out a section of data and drop it into shared memory. It can pick it back up out of shared memory and drop it back into your memory, just inserting it right with all the strides. It'll even pad out of bounds values so you don't get junk. It's amazing. I've been bringing up cooperative groups a lot while talking about clusters, and I figured I should give you an overview of what it's all about. It's CUDA's hierarchical programming model, which was created to allow you to define subsets of threads and operate locally among those subsets. It's literally CUDA's way of programming locality. It's been around for 4 or 5 years because we knew this locality thing was coming. This isn't like some suddenly new revelation or anything like that. We've turned to cooperative groups as the way to control clusters because it's literally built for it. It's literally built for hierarchy. It's a CUDA C++ header-based class library. You include files and you just get it. So there are no dependencies. And it's designed to solve a lot of the tricky problems that show up in hierarchical programming. Things like, how do I say that I require a certain level of hierarchy to do something? Or how do I find out what level I'm at? And the basic idea is the system gives you a reference to the top 3 tiers of parallelism: your block, your cluster, and your grid. And you can either use them directly, do a whole cluster program, or you can subdivide your work hierarchically beneath them to do producer, consumer, or task parallel jobs inside of them. Remember how at the start I was saying you want to work at the level that makes sense for your problem and not think about other levels? It's built to let you do that. Right? If you want to use a cluster like a giant thread block, you can always synchronize any group. So you can just synchronize the threads at any tier of the hierarchy. So I can use my cluster just like a giant block, use the distributed shared memory just like a big shared memory, and my program just looks and feels the same way. Right? You can synchronize threads at all tiers of the hierarchy, but from a block and below, you also get parallel collective operations, reductions, and prefix sums, which are really sort of like the core requirements for a parallel program. Cooperative groups also lets you define groups which are not native to the hardware. Right? So a multi-warp group like this one I'm showing here, I'm inventing a quad warp, which is 128 threads put together. It literally makes a mini sub-block out of my block, and I can synchronize locally, and then I can resplit it again into other smaller partitions. So I can keep on hierarchically doing it, nesting it all the way down. And I can merge any number of 32 thread warps together. So as, supported tiles go from 64 to 512 threads. I said a moment ago that CG, as we abbreviate cooperative groups, CG helps with a lot of the tricky problems of hierarchical programs. Right? In particular, composability is usually a big problem. Some functions absolutely must have the right number of threads. I'd never do a radix 128 FFT without 128 threads, for example. It would be crazy. So without cooperative groups, it's hard to force it. I can name the function something obvious, but I can't guarantee that the user will call it the right way. Cooperative groups explicitly names group types and functions. So my FFT function in the middle here can literally, in the type system, require that I have a group of 128 threads, and that's what it needs to run with it. And then it uses that group to handle sync internally. So as an example of how this hierarchical thing works, and again, drawing on my fluid mechanics background, it's all a matter of scales, right? You always start with a smaller scale and work your way up. And so at point 1, I'm launching a grid of 16 clusters, and 16 clusters with 4x2 blocks is 128 blocks, right? So you'd be bigger in real life, but it's hard to draw more than that. So the example has 16. So then I would immediately jump in and solve all 128 blocks independently. That's massive parallelism straight out, before stepping up at step 4 to my local cluster. Right? This would run my blocks at cluster scope. That's 8 blocks within my cluster. And then I'd step up to my grid stage in step 5, and now I'm synchronizing 16 clusters. I'm never synchronizing 128 things together. By localizing my work and by working hierarchically, I've divided and conquered my problem. Here's another example. This is one I like a lot. I'll take my task parallelism dependency graph again. And for a problem of the right size, I can imagine mapping it onto a cluster, very much how I was showing at the start of this talk, right? I can create separate domains, and my green side is the producer, and my blue side is the consumer in this graph. And I can run each side completely independently, and I can just synchronize across my grid to resolve the dependency. So this would be a GPU scale resident producer consumer system using clusters. Now, the same mechanism, if it's smaller, can be scaled down to apply inside a cluster. I can dedicate some of my blocks to the green producer, other of my blocks to the blue consumer, and then cooperative groups gives me all the tools to synchronize and share data between them and so on. And I can zoom even further in, right? If I want really fine-grained task parallelism, I can break the block into pieces. Here I'm ganging 128 threads together as the producer and 384 as the consumer. I can synchronize and operate locally again until I need to move back up that level. So I can go right down to the individual groups of threads level. And again, borrowing an example from Vishal and Guillaume's talk on Hopper performance, they applied this producer-consumer mechanism to a quantitative finance problem. Called the Longstaff-Schwartz pricing model. You can see their talk to learn exactly what's going on here. They have a whole thing. But I wanted to show you that this isn't just all theoretical. There's a lot of real-world producer-consumer problems out there. The middle bar is what whole cluster synchronization brings you. And the extra 10% comes from having localized my synchronization, right? It looks like just 10%, but that's actually a gain of about 10 milliseconds, which is 1/3 of the original non-cluster time. So localized synchronization makes a really significant difference to the performance of real-world things like this. So shifting gears a little, I want to talk about some of the things we've been doing in CUDA since last year as well, and some of what's coming up. It's interesting. We've been having requests for 128-bit support. It's usually for things like fixed point arithmetic in the kind of finance situations from the example right before. Right, 128-bit integers are already supported in compilers like GTC, and so we've made CUDA C++ aware of it as well, and we've plumbed it through as a full first-class maths primitive with all the arithmetic and logical and other operators. We've also been putting a lot of work into improving compiling times, especially for runtime compilation, which is where you present code to CUDA and it compiles it on the spot and just runs it. Right? That you feel particularly because that compilation time is part of the application time. So we've streamlined the internals of both the CUDA C++ and PTX compilers. So we've made better overlap. We've gone from sequential to pipeline from top to bottom on that left-hand graph. And we've also made the runtime compiler multi-threaded, right, which can halve the compilation time if you're using more CPU threads. So really helpful to get speed ups there. Probably the biggest news on the compiler front is support for C++20. That's coming out in the upcoming CUDA release, CUDA 11.7, which is really soon. It's not yet going to be available on Microsoft Visual Studio. That's coming in the following release, but it means that you can use C++20 in both your host and your device code. There's a couple of caveats, things like modules. There's going to be a blog post going out over the details, so I recommend you look at it and see if this is the kind of thing you're interested in. Another language feature which we've added is the ability to mark a kernel parameter as constant. Right? If it's read-only, the compiler can be conservative and not know what's inside a structure, for example. And so it'll start replicating that structure for every thread. If you define it and declare it as constant, what it'll do is it'll make sure that that parameter is uniform for the whole grid. It's only stored in one place, and you get the advantage of good caching and other performance benefits, and you avoid replicating data structures for each thread. And last but not least, and I think this might be actually a good segue to my next topic, we've been working on link time optimization for kernel codes. I talked about this extensively in November, but I really want to refresh your memory right here, because effectively it takes two pieces of code and it inlines them together to make them one. Right? It avoids the function call overheads, and inlining is such an important optimization of the GPU that for something like this FFT example, we see almost a factor of 2 speed up in some cases. Right? For me, it'll change the way I develop GPU projects to be more modular, since I no longer lose anything when I link them together. Which brings me to libraries. I love this plot, although it kind of looks like a wave. What you're actually looking at is the effect of invoking math functions, in this case the fast Fourier transform, directly from within your kernel code, instead of having to launch them as a separate kernel. Right? This means I don't have to stop what I'm doing on my previous kernel, save the data, invoke an FFT, which then reloads all of my data and works on it. I can just inject the operation that I need right where I need it. And what's really cool about this is that small FFTs, which are the worst case for kernel launches because they take no time and launch cost dominates, they're the best case for device extension because a small problem is exactly what I need to solve from the locality of my thread block. Right? I love it when we flip the cost function on something like this. And just look at the performance coming from those small FFTs. Operating locally inside a single block is several times faster than operating on larger data. So it's my favorite locality theme coming in again. Device callable libraries aren't only faster, but they're much nicer to program sometimes. They mean you can fit them into your existing code. So if you need something like a matrix inversion, you can just drop it in the middle of your code. It's not like a function call, it is a function call. Right? The graph on the right shows how much benefit this is. Again, it's for FFT because that's what's released right now. We're working on cuBLAS and cuSolver as well. Keeping the computation on the GPU with a minimal call overhead is such a big win. And it's all based on the link time optimization I was telling you about a moment ago. Speaking of doing mathematical operations from your kernel code, probably one of the most common questions I'm asked is how to use tensor cores from CUDA programs. And the answer is Cutlass. Cutlass provides you with C++ template functions which allow you to define the matrix and tensor operations you want and then it emits the optimal code for driving the tensor cores at peak performance. Right? Whether you want to inline it deep in a kernel or create a standalone matrix operation or put something in a stream with a CUDA graph, Cutlass has a template for it. We use it internally all over the place. It doesn't require linking. It's an open source header file library you can compile straight into your code. I put the GitHub link at the bottom. Really interesting. If you want to access tensor cores, this is the way that you do it. So if you've watched me give these CUDA talks before, you'll know that one thing I love is people doing really clever tricks with tensor cores to speed up operations they shouldn't be able to work with. Right? If you remember, I talked about the tensor core iterative refinement solver a year or two ago. This is different in that it's not iterative, but it definitely comes under the abuse of the tensor cores heading. What some clever people figured out was that if you have a reduced precision thing like TF32, which is like FP32 but with fewer bits in the mantissa, then you can just do a couple of extra calculations to keep track of the rounding error and adjust for it back at the end. It's brilliant. Right? 3 TF32 operations produce a result that's actually better than doing the calculation and accumulating the result natively in full 32-bit. The graph on the right shows what I mean. The blue curve is for the 32-bit accumulation, which accumulates over time. The green line shows the lower precision tensor cores are still giving a higher precision number. It's not formally IEEE compliant, but the accuracy of the result is far better because it compensates for the rounding errors. So not only is it a better result, but the achieved performance on the left is more than double the official 32-bit floating point operation. So I'm getting out of my tensor cores, I'm getting a better precision at twice the performance than I would be just using native FP32. So check out my colleague Matt Nicely's talk on libraries. There's a ton of stuff going on there. He talks about some of this stuff as well. So my own history in NVIDIA is kind of funny. I joined and worked in CUDA for several years, and then I left to work in industry for a few years. So I went from being a CUDA creator to being a CUDA developer, which is a really interesting experience. It makes you honest in interesting ways. One thing I brought back with me, though, was that the tools make or break a platform. Right? CUDA puts an unbelievable amount of effort into its tools. And so I just sat down and drew the high-level family diagram to show you the extent of all the stuff that's going on. And inside each of these is so much functionality. One thing that NVIDIA merging with Mellanox has brought us is incredible expertise in networking. We've added a ton of network profiling options so that you can investigate not just what your GPU is doing, but what the whole communication layer is doing as well. So UCX is an open source communication framework, and it acts sort of as a common library and API for high-level communication libraries like MPI and OpenSHMEM. The tools can now intercept calls into the protocol layer, which means you can see the call to MPI send up on the left-hand side, and the respective non-blocking UCX operations that are spawned from it. Right? So it's really helpful to be able to see where the latencies are coming from in your communication stack. I would have loved to have this back when I was being a CUDA user, so I really wanted to share this with you. Insight Systems has added NIC performance metrics for ConnectX NICs to its system view. I love this tool. It's so incredible. It's so helpful just to see my entire platform lined up on a timeline. And the thing that's been missing is the networking layers, because so many things are triggered by the network. It'll also track network congestion, all sorts of things. My colleague Yaki Tebeka has a whole talk on all the things that have been done here, and including the two things I've just showed you. So go and check out his talk. It's linked below. The problem with this whole talk is there's just way too much stuff to cover. The tools have added so many things, and honestly, the best thing you can ever do for your CUDA skills is to sit down and spend a day or two learning the tools. Nsight Compute has added a ton of material again, and I can't even scratch the surface. What I can do is I can point you at talks. So at the bottom here, you're seeing all these links. Go and check out these talks for more information and more detail on all of these types of things. In the same spirit of a couple of days learning tools being the most useful time you could have spent, I want to spend a little time talking about NVTX. Right? It's a really simple library for annotating your CPU code with what we call markers and ranges. These are flagging regions of your code to the tools, so the tools are activated and deactivated around them. It means you can very precisely insert some checkpoints into your CPU code and get precisely the breakdown of profiling around your code as you want. It's on GitHub at the link at the bottom of the slide. I've got a simple example on the left here, and I'm just going to quickly walk you through how it works, because I think it's a really cool tool. So ranges behave like stacks, right, in that they nest, and I can have ranges inside ranges. That's helpful in a way you'll see around just in a moment. Right, so I've overlaid the visual profiler output here, so you can see that when I push a creating CUDA context range and pop it after context creation, it shows up on my timeline. Right, I've got the visual breakdown on the top and the exact timings in the event view down below. The next push is around my launch loop. That loop is going to launch 3 kernels. And again, you see the start trigger coming up in the event window. But now I'm nesting ranges from the range push inside my kernel launch function. Right? So you can see that these show up as 3 launches on my profiler. And they show up as three events in the stack timings in the event box. It's such a simple thing to do, and it's so powerful. And if you're not using the tools, if you're not going plugged in, the overhead is completely negligible. Right? It's just like 3 instructions or something. This is such an easy way to zoom in on exactly the parts of your application you want to investigate. And the way it integrates with all the tools is just fantastic. Like I said, learning to use the developer tools will be a couple of incredibly well-spent days. And don't forget to check out NVTX while you're at it. So let's change gears from looking inside your code to looking inside how a CUDA binary works. This is one of those interesting details which has been around for a really long time, doing just fine, but it's starting to show its age, and it's been in need of some attention. It's another aspect of the way that as applications and libraries and GPUs get bigger, it affects the way that things run or the way that you want to run them, right? So let's take a typical Hello World application. This example right here might be exactly the same code that was the first ever CUDA program that you wrote. We just compile it down to an executable. Now, if I look inside the binary, I've got 3 sections. I've obviously got CPU code section, which contains the executable code for main that the operating system is going to load up and jump to. I've got a GPU section, which contains the GPU code for the Hello kernel. The CUDA driver takes this and uploads it onto the GPU to run the program. And I've got a third section, which is the PTX assembly listing that CUDA compiles when running on future hardware. I'm not going to get into that right now. So let's change the example to be something which calls cuDNN to do a simple convolution. This links in the giant cuDNN library. It has something like 10,000 kernels in it. So when the time comes to run the program, I'm basically loading cuDNN. It's so much larger than the rest of my program, usually, that really cuDNN is what dominates. First, the CPU loads it off disk into memory, obviously. We've measured this, and it takes up a bit shy of 2 gigabytes of host memory. Next, the CUDA driver kicks in. Right? It uploads all the kernel code in the library to the GPU. The key here is that it's all the kernel code, whether the program itself needs all the functions or not. Right? This makes sense most of the time, because most of the time you probably have a relatively small library or a relatively small function. It means you can launch whatever kernels you want as quickly as you want. But obviously, when we're talking about over a gigabyte of cuDNN kernels, it might not be quite the ideal thing to do. So sometimes it is, sometimes it isn't. So we looked at this, and we figured there's probably a better option that you might want than everything. And so what we've done is we've added the option to only load kernels when they're accessed. At first, it uploads nothing. And then when I call cuDNN convolution, it starts uploading the kernels as they're referenced. We call this lazy loading. And because sometimes you'll care and sometimes you won't, we're starting by giving you an environment variable to control it. Right? For my trivial cuDNN example, the numbers look great. Half the time to load my binary, a quarter of the memory footprint. Obviously, your mileage is going to vary depending on the complexity of your program. But on the assumption you're probably not going to reference all 10,000 cuDNN kernels, you might want to give it a try. There's an obvious trade-off here. Right? The first time you reference a kernel, it takes a little longer than usual because it does the upload on demand instead of at the beginning. You've traded loading everything at startup to only loading the things you need, but at runtime. You can decide what behavior you want. Give it a try. It's an environment variable. I always try to drop in an update about CUDA graphs because it's both beneficial to performance and it aligns well with the task parallelism story I've been telling you. Right? A general thing that we're working on is to try and allow more sophisticated management of how a graph executes, right? So that you can tweak it as you reuse it to get different behavior. So the 2 things we've added recently is the ability to enable or disable individual graph nodes before you launch a graph. That means I can launch a graph one way, change what runs internally, and launch it again. Right? So in this example, where B is forking into C or D, I can disable one of them. So let's say D in this example. So I can just say, I want my graph to run A, B, C, E. And so my fork is no longer a fork. It's really just a way for me to select without having to rebuild the whole graph. I can do this at very low cost for full graph launch. On the right-hand side is something which is maybe a little more obvious. Prior to now, a graph simply inherited priority of the stream that you launched into. We've now added the ability to specialize individual nodes based on priority. This is because graphs tend to represent large, complex workflows. And so you often want to express that complexity in the graph structure itself. And finally, I want to look ahead to something else that I'm really passionate about. And that's bringing CUDA C++ closer to standard C++. Right, a few years ago, we launched the CUDA C++ standard library, which we call libcu++. I've told you about it before. It's a strictly conforming implementation of the standard library, which is heterogeneous, so that your STL programs will be able to span the CPU and your GPU kernels. Heterogeneity moves strongly in the direction that C++ itself is moving in, right, which is starting to enable parallel algorithms and asynchronous execution as first-class components of the language. So I'm going to spend a moment to tell you about what I see coming there, because it's pretty exciting. I think by far the most exciting move for standard C++ in that direction is work the C++ committee is developing called senders and receivers. Right? This is a framework for orchestrating parallel execution and writing your own portable parallel algorithms, with an emphasis on portability here. Right? This framework will provide portable and unified abstractions for parallelism, for asynchrony, concurrency, and I/O. Right? The idea with senders and receivers is that you can express execution dependencies and compose together asynchronous task graphs in standard C++, as I'm showing on the left. Right? This is a complete solver for Maxwell's equations composed of a series of scheduled operations. What's really interesting to me is how this interacts with heterogeneous systems. Right? Senders and receivers will unify work launch across a different range of targets and programming models. For example, it'll provide a unified way to launch work on a thread pool or on a fiber, or with OpenMP, or using any of CUDA's various launch mechanisms, regular launch, cooperative launch, graph launch. This is an example of that unification of work creation. With a single dispatch command, sync wait, I can target CPUs or GPUs, single thread, multi-thread, even multi-GPU. Right, it's an amazing project. My colleague Bryce Adelstein-Lelbach is giving a talk on this, which I strongly recommend going to see, and I've linked below. Some colleagues of mine helped apply senders and receivers to a code by Jonas Ladd at the University of Geneva, simulating multi-component flow through a porous medium. The code runs on Palabos, which is a framework for parallel computational fluid dynamics using Lattice-Boltzmann methods, and it looks at how carbon dioxide is sequestered in sandstone. Right? You can see from the chart on the right the amazing scaling that can be achieved using senders and receivers targeting a multi-GPU scheduler. Unfortunately, that's all I have time for. There's just so much to say. I can only ever touch on a subject. But what I can do is I can leave you with a list of references to other talks, sessions, materials, things like that, where you can look and find out about all the things I've gone over today. Thank you all so much for your time and attention. I really appreciate it. And I will see you next time. Have a great GTC.